Look at that concrete pump truck on screen. This stuff is everywhere. In cities, you're standing on it, driving over it, and living inside it. Concrete is often called the world's most used human-made material, and you'll even hear it described as second only to water in sheer use. Here's where we're headed. Watch the quick roadmap on screen. We'll chase the mystery of Roman durability, unpack why modern cement carries a huge carbon footprint, and visit the self-healing concrete ideas that are finally leaving the lab. But first, a common mix-up. Cement and concrete are not the same thing. Like baking, cement is the flour, concrete is the bread. Cement is the binder, the glue. In a typical concrete mix, it's only roughly 10 to 15% by volume. Most of what you see is sand and gravel plus water. And that small slice is the problem. In 2024 alone, the world produced about 4 billion metric tons of cement. Because of how it's made, cement is responsible for roughly 7 to 8% of global CO2 emissions. It's not just the heat. Making cement also releases CO2 from limestone itself. Zoom out and the scale gets surreal. Humanity is adding something like a Paris-sized city of new floor space every week for decades. Yet plenty of modern concrete, especially in harsh conditions, can show serious deterioration within a few decades, while parts of Roman marine concrete are still holding up nearly 2,000 years later. So did we forget how to build? Or did the Romans stumble onto a chemistry trick we're only now learning to read? Let's ask our historian, starting with what you're looking at, the Pantheon's oculus, still crowning a concrete dome after nearly 2 millennia.
Rome didn't just inherit stone. They engineered a new kind of rock. On screen is the Pont du Gard, cut stone, not concrete, but it's the same Roman story of durability. And then there's poured concrete, like the Pantheon's dome, still standing nearly 2,000 years later. So why do some modern concrete structures need major repairs within decades?
I've always heard it was the volcanic ash, or maybe they just built thicker walls.
Those matter. But the clue is hiding right in the mix. Look at this close-up. See the bright white chunks scattered through the mortar. Archaeologists call them lime clasts.
I've seen those in photos. I honestly thought that was just sloppy mixing, like they didn't stir the batter enough.
That was the assumption for a long time. But if the same mistake shows up again and again in long-lasting Roman mortar, you start asking whether it was intentional.
The big clue came from Pompeii, a house mid-renovation when Vesuvius erupted in 79 CE. Basically, a work site paused on the clock. A study published on December 9, 2025, analyzed the raw materials left there and found strong evidence the workers were using a technique researchers call hot mixing.
Hot mixing, like they heated the water?
No, the chemistry makes the heat. Quicklime is calcium oxide. When water hits it, it hydrates into calcium hydroxide and releases a lot of heat. That burst of heat changes how the mortar forms and helps create those white lime clasts, porous little pockets of reactive calcium. If you want a metaphor, they're like chemical batteries.
Batteries? What are they powering?
A self-repair mechanism. Think of each lime clast as a reservoir of reactive calcium. When tiny cracks form and water seeps in, the clasts can dissolve a bit. That calcium-rich solution moves into the crack and, over time, minerals, often calcium carbonate, reform and help seal it.
In lab tests with Roman-inspired mixers, researchers have watched cracks stop leaking within weeks, sometimes in about 2 weeks.
That is incredible. So the water that usually destroys modern concrete actually saves Roman concrete.
In small cracks, it can. Modern reinforced concrete has a different failure cascade. Once it cracks, water and salts reach the steel. The rebar rusts, expands, and the concrete breaks off around it. Roman concrete didn't rely on steel reinforcement, and its chemistry can keep evolving.
And here's the irony. Vitruvius, the Roman author on architecture, described slaking lime first, then mixing mortar. It's the neat, write-it-down version, but the Pompeii evidence suggests builders didn't always follow the textbook. Dry piles of quicklime and volcanic ash were ready to be wetted and used on site. The real innovation wasn't just in libraries, it was in workshops.
So the builders knew something the writers didn't. If this tech is so good, why aren't we using it for everything today? Why are we still dealing with crumbling bridges?
Scale and schedules. Modern construction optimizes for speed and predictability. Roman-style binders can be slower, and natural materials vary from place to place. Harder to standardize.
And I assume there's a catch with the emissions too.
Unfortunately, yes. Making lime or cement means heating limestone, and that process releases CO2. And that is where the chemistry trap begins. We need to talk about the invisible trap inside concrete. When people picture concrete emissions, they think about mixer trucks and job site equipment, and those do matter. But the biggest hit usually happens earlier, in a kiln, because of chemistry.
So if I'm looking at a sidewalk, the pollution isn't mainly from the fuel used to pour it. If cement starts as rock, why does it end up emitting so much CO2?
Because cement is the glue, and making that glue is the hard part. To make Portland cement, we heat limestone, calcium carbonate, with other minerals. First, you drive off CO2 in the calciner. Then you push the material hotter, up around 1450 degrees Celsius, to form the glue precursor called clinker. Hotter than most lava flows.
Okay, that explains the energy bill. You need a lot of heat to run a kiln at those temperatures.
Exactly. And that's only half the problem. Even with zero carbon heat, you don't get to zero. That's the chemistry trap you're seeing on screen. CaCO3 breaks apart into CaO, what we want, and CO2, what we don't.
So the rock itself is the CO2 source.
That's the right mental picture. We call them process emissions, and they're typically the majority, around 60% from the chemistry, versus about 40% from the heat, though it varies by plant and fuel. And here's the culprit. Those dark, marble-sized nodules in the shot, clinker. The more clinker in your cement, the bigger the carbon bill.
And that's where the modern world diverges from the ancient one. The Romans used lime and mineral additives, but they weren't running rotary kilns to mass-produce Portland-style clinker at today's scale. Seeing a modern plant on screen makes the contrast feel enormous.
The scale is enormous. Cement is responsible for about 7% of global CO2 emissions. And, on average, making a ton of cement releases on the order of 0.6 of a ton of CO2, mostly because of clinker.
So we can clean up the heat, but we can't electrify away the limestone splitting. Solar doesn't stop that CO2 from forming.
Precisely. Efficiency helps, but chemistry sets the floor. So the options narrow to 3 levers. Use less clinker, switch to new binder chemistries, or capture the CO2 before it leaves the stack.
That's a serious engineering menu. So let's start with the first lever, using less clinker. What does that look like in the real world?
Here's the reality check. There's no single magic green concrete. Think of it as a 3-item menu. Cleaner cement ingredients, capturing the CO2 we can't avoid at the plant, and smarter design so we pour less in the first place.
I like a good menu. Let's start with the main course. What is the biggest lever we can pull right now to cut those emissions?
The biggest immediate win is changing the recipe, cutting down the clinker. A leading option is LC3, limestone calcined clay cement. In a typical LC3 blend, you replace roughly half the clinker with calcined clay and ground limestone.
So you're diluting the carbon-intensive part with clay. Does that actually make a dent in the CO2 numbers?
It can. Across many life cycle estimates, LC3 often comes in around 30 to 40% lower CO2 than ordinary Portland cement, mostly because you make less clinker, and the clay is calcined at much lower temperatures than clinker. And it's not just lab work anymore. In 2025, Noida International Airport in India announced it was using LC3 at large scale in its construction.
Okay, 40% is great, but that still leaves 60% of the emissions. We still have to burn fuel to heat the kiln, right?
Exactly. That's where the heavy artillery comes in. Carbon capture and storage, or CCS. If we can't stop the chemistry from releasing CO2, we capture it before it escapes the stack.
I feel like we've been talking about carbon capture for decades. Is it actually working at scale now?
It's starting to, especially in cement. The Brevik cement plant in Norway inaugurated its CCS facility on June 18, 2025, designed to capture about 400,000 tons of CO2 per year. The CO2 is captured, liquefied, shipped, and stored in subsea reservoirs under the North Sea through Norway's longship value chain.
That sounds expensive, but necessary. Now, let's move from the chemistry to the actual building site. I keep seeing 3D printed houses on my feed. Is that just a gimmick, or is it a real solution?
It started as a novelty, but it's becoming a real efficiency tool. The climate win isn't the robot by itself, it's the geometry. You can place material only where it's structurally doing work, and sometimes reduce formwork waste along the way.
So you save waste because you don't have to build a box to pour the concrete into.
Precisely, and we're seeing real projects. In Georgetown, Texas, the Wolf Ranch development is building 100 3D printed homes. And Starbucks opened its first 3D printed US store in Brownsville, Texas in May 2025. The caution is that printable mixes can be cement-rich to pump and set, so printed doesn't automatically mean lower carbon.
If you use a high cement mix to print a wall, you might accidentally increase emissions, right?
That's the risk. The future is combinations. Print a shape that uses less material, pair it with a lower clinker binder like LC3 where it fits, and capture the remaining process CO2 at the plant. We need the whole toolbox.
It seems like concrete is finally entering the 21st century.
It's about time. We're taking a material that built the ancient world and reinventing it to hold up the modern one.